A while ago, I made a video titled, "What is Anderson Localization?" and in it I discussed the Anderson model and the Aubry-Andre model. I chose to leave out any numerics or mathematical work in favor of looking at the phenomena from a dynamical perspective. So today, let's fix that. These two models can be written in the following way, where the Fj daggers are fermionic operators associated with the lattice site J with the usual anti-commutation relations. If you would like a more detailed explanation of fermionic operators, check out my Jordan-Wigner transformation video or solving the XX model video. By the Hamiltonian, you can see that we have chosen open boundary conditions by the fact that we don't have a hopping term across the boundary. L in the sum is how many lattice sites we will let the fermions potentially sit in. J here controls the hopping strength and could be positive or negative. The most important part is the on-site potential term coming from lambda subscript j. In our video on the XX model, this was constant for all lattice sites. For the Anderson model, this is a random variable randomly generated from a uniform distribution, where W here is the disorder strength. In the Aubry-Andre model, this term is the following cosine expression, where sigma is an irrational number. The constant lambda here dictates the disorder strength. So the following method that I'm about to do would solve all of these models numerically. In the XX model video, we saw that if we have periodic boundary conditions, we could just do a discrete Fourier transform on the sites to solve the model. Unfortunately, in the disordered cases, this no longer works. Okay, so let's solve it. First, we will rewrite our Hamiltonian in a more compact form, writing it as the following, where M is a matrix where on the diagonal we have all the lambda subscript i's, and on the immediate off diagonal it is filled with the parameter j. All other entries are 0. From here, it might be fun to define the column vector of our annihilation operators. So with these two ingredients, we can rewrite our Hamiltonian in the following expression. Since M is a real symmetric matrix, we can diagonalize it like the following, where A here is a real orthogonal matrix, and D is a real diagonal matrix with entries D subscript II is equal to epsilon of I. We then define new fermionic operators by the following expression. So this gives us new fermionic operators that we can write in terms of the orthogonal matrix and the original fermionic operators. The raising operators can similarly be found by simply taking the Hermitian conjugate of this expression. One can easily reverse this transformation and find the expression for the real space fermionic operators F subscript j. But this then allows us to rewrite our Hamiltonian as the following expression. So this is just a sum of number operators with potentials or eigenmode energies epsilon subscript k, so this model is solved. The eigenstates can be constructed by starting in a vacuum state and applying the dk dagger fermionic operators to fill the state with fermions in this D space or this transform space. You can verify that these are indeed fermionic operators by verifying the anti-commutation rules using the orthogonal transformations properties. For example, for the raising and lowering operators, you can figure out that you get the following expression. So this is all very interesting, but oftentimes we are interested in understanding dynamics in this context. So let's work out how to do that. In the Heisenberg picture, we can evolve our D creation and annihilation operators quite easily. So here's the equation for an annihilation operator, where we have, as always, set h bar is equal to 1. From here, using the fact that the anti-commutation relations are the following, and that any fermionic raising or lowering operator squared is always 0, we can easily see that we get the following expression for the time evolution. So what kind of states would we be interested in covering? Well, for one, the eigenstates of the model can be written down as the expectation value of the number operators in this D space. And these number operators will either have the value 0 or 1 for a eigenstate. If we were to look at correlations or expectation values of these operators for different values of k and L, if k does not equal to L, then this expectation value for eigenstates would always be 0. So a ground state, for example, would choose to turn on all of these fermions in the eigenmode space, or D space, such that epsilon k is less than 0. We could also have a thermal state, which would just be the Fermi-Dirac distribution. We could also be interested in an initial configuration where we know the initial conditions of fermions in real space. So perhaps we would know the expectation values being either 0 or 1 on different real space lattices. In the Anderson localization model example, we simply set one single fermion in the middle of real space and watched it evolve throughout the lattice. So with all the ingredients that we've covered up until now, we could reproduce the results of that video quite easily. So let's work out an example. First, let's say we know that our state is in a product state of fermions in real space. So we know that the number operators, fj dagger fj, the expectation value is either 0 or 1. The first thing we need to do is figure out what the expectation values of dk dagger dl, what these expectation values would be in eigenmode space, or D space. From there, we can then evolve our system. So that's easy. We just use the orthogonal transformation. And since we are in a product state, only the terms such that I is equal to j survive here, so this reduces to the following expression. So here we see that we have everything on the right-hand side, so we can figure out numerically what the expression is for the left-hand side expectation values. Notice that the product state has non-zero terms for the D operators, or the eigenmode space operators, when k and L are not equal. In general, all of these terms will be non-zero for any choice of k and L you make, which means, obviously, we are not in an eigenstate. So this defines our initial conditions, and we can now start time evolving, knowing exactly what our initial conditions are. So let's say, for example, we wanted to track a number operator on the lattice as it evolves in time. To do this, we can use the reverse transformation as seen here. Once you have this expression, adding time evolution is easy. You just evolve the D space creation and annihilation operators, which we solved previously. And with this, you track the number operator on site J for all time. So this is pretty easy, right? Let me know if you have any questions in the comments about how this works. So there's definitely a lot you can do with this. In fact, you could probably reproduce the dynamics shown in my Anderson localization video. But that's it for today, guys. I hope you liked the video. If you did, feel free to like, subscribe, and leave a comment below.